It is essential for us, beyond recognizing that there are only n distinct discrete frequencies in the DTFS, it is still essential for us to understand what the values of these frequencies are and what range of values they lie within. It is with this in mind that that we shall go and re-examine the different complex exponentials that are associated with each of the discrete frequencies. So, let us recall what the coefficients are. We have the component complex exponentials are. The first one is e to the j 2 pi by n into 0 into n. This is the first member. This is what we have called phi 0 of n. Then we have e to the j 2 pi by n times 1 times n, which is what we call phi 1 of n, and so on until we get e to the j 2 pi n minus 1 by n times n, which is phi n minus 1 of n. That is already given us n different frequencies, but just for exploration's sake, let us see what the next member will be. The next member is e to the j 2 pi n by n into n. Now, what are the frequencies associated with each of these? The normal format of the complex exponential or of the purely imaginary exponential, as is this case, is there is the time index, which might be discrete or continuous, then there is the frequency index. In this case, this is the frequency index. Sorry. This represents the frequency. Here, for example, this gives the frequency, and so on until you have here the frequency given by this and here by this. So, that is what the frequency is supposed to represent. The frequencies, as you can see, run from 2 pi by n, the smallest number, which I will call omega naught, 2 pi by n, 2 pi by n into 0 is omega naught, 2 pi by n into 1 is what I will call omega 1, which is the fundamental frequency. This is the 0 frequency. Then you have 2 pi into 2 by n, which we will call, say, this is exactly twice the previous one. So, it is 2 omega 1, and so on until you come to 2 pi n minus 1 by n, which we will call n minus 1 omega 1. All right. Now, this is not common convention. So, I will just make a slight change in what I have just said. I will just call this the 0 frequency, and I will call this as omega naught. This is the fundamental frequency. So, this becomes 2 omega naught and so on up to n minus 1 omega naught. So, these are the frequency components. As you can see, the values vary from omega naught to n minus 1 omega naught, where omega naught is essentially 2 pi by n. So, the smallest non-zero frequency is 2 pi by n. The largest non-zero frequency is 2 pi times n minus 1 by n. So, they are all some fraction of 2 pi and they range from 0 to 2 pi times n minus 1 by n. For large n, you can see that the largest non-zero frequency will become very close to 2 pi, and this finally tells us what the frequency axis should be like. It should be running from 0 to 2 pi, and on this we will plot these coefficients of the DTFS, namely x 0, x 1, where this is 2 pi by n, then we have say x 2 occurring at 2 pi 4 pi by n, and so on until just before 2 pi we have x n minus 1 corresponding to 2 pi n minus 1 by n. So, the largest available frequency largest possible frequency in the representation is 2 pi, and even this is really not achieved except for very large values of n. So much for giving a physical interpretation to the notion of frequency. If you want a even more closer understanding of this, then we must start with setting a certain analog frequency, a continuous time frequency value, and then measure the rate at which this signal of continuous time is sampled to obtain a discrete signal, and understand things from there. That is too much matter to get into at this stage. We will be doing it when we talk about the theory of sampling and reconstruction. Right now, we see that discrete frequencies take on discrete values omega naught 0, omega naught, 2 omega naught up to n minus 1 by n omega naught, and all these lie within the range 0 to 2 pi. With this understanding of discrete frequencies, we know how to make a spectral plot. It will be something like this. For example, for x n, you could have for x for the frequency plot of the Fourier spectrum would be something like this, line spectrum. This is what we have. It is only a line spectrum. Next, we want to see what is the common way in which the discrete time Fourier series is used. You see, the discrete time Fourier series, as I have been saying, deals with periodic discrete time signals. Periodic discrete time signals. But another way of looking at a periodic signal is to call it a finite support signal, or what is called a signal of finitely many points, and this is the nomenclature and terminology that is used in what is called the DFT. Finite support signal of a support of n points. Now, in the first case, we would say that the signal repeats itself an infinite number of times in all directions. The same n points of the signal are repeated. In the second case, we just say that no, the signal is only defined for n points. We are not saying that it is 0 outside those n points. We are saying that it is defined only for n points. Once we make that definition, that it is defined only for n points, then lots of things become much simpler. For example, we can say, since the Fourier transform, the DTFT, the DTFS, the discrete time Fourier series of this sequence has also n coefficients, capital N coefficients, and they too are periodic. It turns out that even there you can take the stand that it is only a finitely supported sequence of transform values. In short, you can say that the DTFS maps n length sequences in n to n length sequences in the omega domain. So, instead of periodic, we are saying it has a finite support. Now, this interpretation is given a different name, it is called the DFT. Standing for discrete Fourier transform. The DFT has a slightly different set of notations. It takes sequences x n for n equals 0 to n minus 1 and maps them to signals x k, as they are called, the discrete frequencies, where k goes from 0 all the way to n minus 1. So, this is the discrete Fourier transform. As you can see, it is only notationally different, and if you wish to write the analysis and synthesis equations of the DFT, you would simply write synthesis and the analysis is x k equals 1 by n summation over n of x n, n equal to 0 n minus 1. So, everything is of finite length now. The impulse response is of finite length, the signal is of finite length, the output is of finite length, everything is of finite length. The next thing we will move on to investigate is what happens if we take a certain n periodic signal or n length signal, depending upon whether we use the DTFS terminology or the DFT terminology, and pad it with an equal number of zeros. What then happens to the Fourier series spectrum? So, let us say that x n or rather x 1 n equals x n for n equals 0 to n minus 1 and x 2 n equals x n for n equals 0 to n minus 1 and it is equal to 0 for n equal to n to 2n minus 1. Now, x 1 n is of length n or has period n. So, you can say if we take the DTFS terminology which we are more familiar with, we can say therefore, x 1 n equals x 1 of n minus n, whereas here x 2 n equals x 2 of 2 n. n minus 2 n, sorry. X 2 n equals n minus 2 n. Let us call 2 n as n dash. N dash. Now, I will rewrite the analysis equations in a slightly modified manner. The analysis equations gave the value of the x k for various values of k going from 0 to the number of points in the sequence. So, we will write first n x k, which is the set of coefficients of x n x 1 n scaled by factor k. N x k equals summation x n times phi k n, phi k star of n as k as n equals 0 to n minus 1. Fine. So, there are n different coefficients available over here, but now moving to x 2 of n, x 2 of n is a 2 n length sequence, is an n dash length sequence. N dash, and hence we will write n x 2 k, this we will call n x 1 x 1 k, n x 2 k will be equal to summation n equals 0 to 2 to the power k of x n x 2 n, here it was x 1 n because x n was equal to x 1 n, x 2 n phi n star of 2 n. This earlier one was, for this one it was phi n. That means, there are n different complex exponentials which combine whose correlations you have to evaluate. Now, there are 2 n over here. So, now the coefficients of these, the coefficients of x 2 of n run from k equal to 0 to k equal to n dash minus 1, which is equal to k equal to 2n minus 1. So, these are the different coefficients you have. Now, we shall denote x x n times x k or x 1 k as x 1 k omega naught, where omega naught equals 2 pi by n. Fine. Then it turns out using similar notation for x 2 also, it turns out that n x 0 k sorry n x 2 0 or rather n dash n x 1 0, which is the 0th coefficient of x 1 multiplied by n equals n dash x 2 0. Then n x 1 1 equals n dash x 2 2, and so on until you get n x 1 n minus 1 equals n dash x 2 2n minus 2. That is to say that alternate coefficients of the DTFS of x 2 are the same as the sequence of coefficients in the DTFS of x 1. In fact, all the even coefficients of x 2 correspond 1 for 1 in magnitude and frequency position with those for x 1, but the spectrum of x 2 n has an additional n points, That is to say that its frequency representation is higher in the resolution than that of x k than that of x 1. Sorry. than that of x 1 n. We have doubled the frequency resolution by padding it with n zeros. If we had padded it with 3 times n zeros, we would have quadrupled the frequency resolution, and so on. In short, as we make n dash tend to infinity, as n dash tends to infinity, 2 pi by n dash, which I will call omega naught dash, tends to d omega, tends to an infinitesimal value. And of course, there are a large number of coefficients now in the Fourier transform. There will be coefficients far more in number than before, until finally, as n dash goes to infinity, we find that the line spectrum merges into a continuous spectrum. It merges into a continuous spectrum. This continuous spectrum, which we will call x2 of omega, is that what I have called it? I think that is what we have called it, satisfies at frequencies k omega naught the relation x2 of omega at omega naught equals x1 of and at omega equal to k omega naught equals x1 of omega naught at k omega naught, and it is non-zero elsewhere, whereas this is 0 elsewhere. By means of this process, we can go on increasing the resolution until it becomes a continuum. When it becomes a continuum, this implies certain modifications in the analysis and synthesis equations. Let us look at each of them. First of all, analysis. The synthesis equation says that x n equals summation x k e to the j k omega naught n, right, and for x 2 k it would be this and a subscript of x 2 k over here. But we have already made the notational change that n dash x 2 k is what we are calling x 2 at k omega naught. If we use this notation, then x 2 n becomes equal to a summation. All the summation is of course overall k. So, I am just writing k over here, overall k of k going from 0 to n dash minus 1 whatever. So, you will get x 2 of k omega naught by n dash, because that is x 2 k e to the j k omega naught n. Now, as n dash increases, as I said, there are closer and closerly more and more closely spaced line frequencies. So, e to the j k omega naught n simply becomes e to the j omega n, and the summation becomes an integration. Finally, you have 1 by n dash, summation becomes an integration, and 1 by n dash is nothing but d omega by 2 pi. Making all these changes and recognizing that integration from summation for k equal to 0 to n dash minus 1 over k equal to 0 to k equal to n dash minus 1 is the same as summation over omega equal to omega naught to omega equal to n dash minus 1 omega naught, which tends to 2 pi. We can write with all these changes that x n or x 2 n, which is now a non-periodic signal because it is of infinite duration, equals 1 by 2 pi integral 0 to 2 pi x dash, or rather x 2 of omega e to the j omega n d omega. But since this x omega x 2 of omega is periodic, which is very easy to show, we could actually integrate over any contiguous period of length 2 pi. For example, we could rewrite this equally as 1 by 2 pi integral minus pi to pi x 2 of omega e to the j omega n d omega. It is equally valid to write this. Now, the analysis equation. We have n x k equal to x 2 n x 2 k, if you like, equals x 2 of k omega naught, was given by summation n equals 0 to n dash minus 1 x n e to the minus j k omega naught n. Applying the same changes over here, we find that as n dash tends to infinity, e to the minus j k omega naught n simply becomes e to the minus j omega n, and n runs from the sum runs from n equals minus infinity to n equals infinity. So that you get x omega equals, rather x 2 of omega equals summation n equal to minus infinity to infinity x n e to the minus j omega n. With this, the spectrum of the non-periodic x n has become a function of the continuous variable omega as it runs over an interval of length 2 pi. So, we have a continuous spectrum, no longer have a line spectrum, but instead a continuous spectrum. We have a continuous spectrum now. However, this spectrum is periodic with period 2 pi, something which we will demonstrate in a moment, but let us at least understand what has finally resulted. What has finally resulted is a frequency domain representation for non-periodic discrete time signals. Where the representing signals namely the complex exponentials e to the j omega n, the periodic complex exponentials e to the j omega n are themselves periodic but can nevertheless represent non-periodic signals x n because they are all no longer harmonically related. This is analogous to the similar discussion that we had for the case of the continuous time Fourier transform. Even there, the representing signals are all periodic signals, but they manage to represent non-periodic signals there, and that again happens because we are actually combining by addition periodic signals which are not harmonically related. So, this is called the discrete time Fourier transform. called the DTFT, whose analysis equation is given by x omega equals summation over all n x n e to the minus j omega n, and synthesis is x n equals 1 by 2 pi integral minus pi to pi, if we like, x omega e to the j omega n d omega. These are the analysis and synthesis equations. Now, let us, with this in place, it is time to discuss issues like the convergence behavior of convergence existence issues of the DTFT. It can be shown that if the sequence, the infinitely long discrete sequence, the non-periodic discrete sequence x n is absolutely summable over all n, then x omega will be finite for all omega 0 less than equal to omega less than 2 pi. And whenever x omega exists, the reconstruction x hat n given by x hat w n, I will say, integral from minus w to w x of omega e to the j omega n d omega for 0 less than equal to w less than pi. This is x hat n. Now, this turns out that limit as w tends to pi of x hat w of n equals x n for minus infinity less than n less than infinity. That is, for all n, the reconstruction matches or converges to the original sequence. Whenever the discrete time Fourier transform exists, this convergence will happen. We only have to take care that existence is ensured, rest of it will follow automatically. Okay. So, this has brought us to a certain level. Now, what can we say next? Examples करेंगे, उसके बाद बंद कर देंगे. At this stage, it would be worthwhile to look at a few examples of the DTFT. examples of the DTFT. Remember that the DTFT exists for sequences which are absolutely summable. So, very evidently we cannot consider sequences which keep blowing up without limit, they should be absolutely summable. So, we will consider such examples of sequences and see what the DTFT comes to. First example, let x n be equal to a n u n. That means it is a sequence like this. A sequence which exponentially decays as n tends to infinity. Now, what would be the Fourier transform of this sequence? The discrete time Fourier transform of this sequence, x omega would amount to summation from 0 to infinity, because for negative values of infinity this is 0 because it is multiplied by u n, and you have x a to the power n, just one second, a to the power n e to the minus j omega n. Now, note that a must be between minus 1 and 1, mod a must be less than 1 for this kind of a graph to exist, otherwise it will be blowing up and not going down. So, mod a is less than 1. Now, when mod a is less than 1 and x omega is this, x omega evaluates to 1 by e to the minus 1 by 1 minus e to the minus j omega. Fine. Next, second example, we will now consider a bilateral signal, a signal which is non-zero for both negative and positive time, and which is also even symmetric, and see how it comes out. Clearly, for the first example, 1 by 1 minus e to the minus j omega is not really a real function. It is complex valued because there is complex numbers in the denominator, and that is understandable for reasons of symmetry that we will come to in a little while. The second example is x n equals a to the power minus mod n. Again, we are going to say that or rather a to the power mod n, you can say, where a is less than 1, mod a is less than 1. Now, in this case you will have x omega equal to summation from minus infinity to infinity. Well, we can split it up into two terms. You will split it up into two terms and get summation minus infinity to minus 1 a to the minus n e to the minus j omega n plus summation 0 to infinity a to the n e to the minus j omega n. Fine. Now, this expression is what we want to find the to evaluate, and this comes to finally, after simplification, it comes to one minus a squared. Actually, let me write the intermediate steps as well. 1 by 1 minus a e to the minus j omega plus 1 by 1 minus a e to the j omega. Going back to the previous problem, there is just a small factor I have missed in the final expression for x omega. If you look at this part, this part is wrong and we are just going to strike it out. I forgot about a. This is equal to 1 by 1 minus a e to the minus j omega. So, this can be knocked out now because it is wrong. This is the expression over here. Here we have similar expressions, but separate expressions for the two parts, and on simplification this becomes actually it becomes 1 minus a squared divided by 1 minus 2a cos omega plus a squared, 1 minus 2a cos omega plus a squared. So, this is the expression for the DTFT of the second example. Now, since the second example is even symmetric, it will turn out, for reasons that we will describe when we discuss the properties of the Fourier transform, that this should be completely real, as indeed it actually is. All terms on factors in the expression for x omega can easily be seen to be completely real. There are no complex terms over here. Now, the third example is of the rectangular pulse. The rectangular pulse is given by x n equal to 1 for mod n less than n 1, equal to 0 for less than equal to n 1, and equal to this for mod n greater than n 1. So, you would get x omega as a finite sum from n equal to minus n 1 to n 1 of x n is anyway equal to 1. So, you just get the basis function e to the minus j omega n. This is what you get, and this comes to be equal to sin omega n 1 minus half omega times n 1 minus half over sin omega by 2 by 2. So, these are a few standard examples of the DTFT of some simple expressions.